Welcome back to ECE 320A. We're in Unit 12, which is our two-port network unit. Homework number 12 is needing to be finished up at the end of this unit, and you're getting your material textbook-wise from Chapter 18. What I want to do now is illustrate how we can use, we're trying to convince you that these two ports actually are a good way to proceed if you're now doing some analysis or design, and it may look a little bit like it's excess work because we're just playing with somewhat trivial circuits, but these two ports do have a lot of power. And what we want to do now is describe how we can now interconnect a source and a load, which we will call a terminated two-port, to this two-port network. And then we'll go ahead and derive one of the relationships, and in this case, I think we're going to do the input impedance of a terminated two-port, but you can identify other characteristics or properties of a terminated two-port. We could identify the output current, I sub 2. We could identify, and we'll get into that in just a minute. But here is the graphical description of a terminated two-port. The two-port is sitting here inside the two ports, and remember we have our port current requirements. I1 has to be going in up top on the left and coming out down below on the left. I2 is at the output port. V1 and V2 are at the input and output port, or port 1 and port 2 respectively. Connected to the input side, port 1, we have a source which might have an internal impedance, Z sub G, and we're just denoting the source as V sub G. That could be either a DC source, a sinusoidal source, a Laplace transform based source. Z sub G is a generic impedance. And then we have some load connected to the output port, and we're classifying that load or labeling that load as Z sub L. And once we have this source and load connected to our two-port, and inside this two-port could be a mess, but we've now parameterized that by 4 different parameters. And we've been focusing on Z parameters, but it could have been Y parameters, it could have been H parameters. Something is sitting in there that relates 2 independent variables of the I1, I2, V1, and V2 to the 2 remaining dependent variables. We could look and try to identify the input impedance, Cn, looking into the input port. We could look from the port 2 terminals and find the Thevenin voltage and the Thevenin impedance. And those are some of the 6 characteristics of a terminated two-port that you can find. As we said, the input impedance, Z sub n, is V1 over I1, or you might want to find the input admittance, which is the reciprocal. Yn is now I1 over V1. You might want to find the output current, which is I sub 2. You might want to find the Thevenin voltage and Thevenin impedance, V Thevenin, Z Thevenin, with respect to port 2. Looking into the output port, you might want to try to consolidate all of that into a Z Thevenin and a V Thevenin, which would be easy then to analyze with different loads, Z sub L. You might want to know what kind of current gain do I have? What's this ratio of I sub 2 to I sub 1? And then you can have different voltage gains. You might want to see what's the voltage gain between the 2 ports on my 2-port, V sub 2 over V sub 1, that you know where those are, or you might want to go ahead and find the voltage gain between V sub G and V sub 2, which would obviously then incorporate the Z sub G. So the voltage gains, you could be talking about 2 different ones, V sub 2 over V sub 1 or V sub 2 over V sub G, and you'll want to make sure that it's clear which voltage gain is being asked for or trying to be determined. And if it's not clear, then state which one you're using and go ahead and perform the analysis. Let's now just illustrate, and in the book you can find these different relationships between Zn, Zthevenin, the voltage gain, etc. in a table, but let's just illustrate where one of those might actually come from. And in this particular discussion, we're going to focus on the input impedance, Zn, which is coming or looking at the loaded circuit or the terminated two-port from the input port side. We obviously have the relationship from our z parameters relating these four variables, v1 and v2. We'll call those equations 1 and 2. We could also perform KVL at the input port since we now have this terminated. We have it terminated on both sides. We can now just do a KVL over here. And that's simply going to give us, as an expression, we now have minus v sub g plus z sub g I1 plus v1 is equal to 0. And I wanted to say 3, but that's equation 3 that I'm going to label. I'm going to now try to find the input impedance looking into port number 1. We can also simply invoke Ohm's law, or we could write a KVL equation at the output. But we know that V sub 2, and here Ohm's law have just keep clear the way that we've defined I sub 2 relative to V sub 2. So typically you would think of the current flowing in this direction from top to bottom, but I sub 2 is labeled just opposite to that, and that's going to then incorporate a minus sign, so that basically at the output side, or in the termination on the output, we have V sub 2 is equal to minus Z sub L I sub 2. And that let's just go ahead and label as equation 4. And what we want to do now is find, using those four relationships, we have our two equations from the z parameters, and now because of the loading we can find a relationship between v sub g, z sub g, and z sub l on the two input and output ports of that circuit. We want to now find z sub I, where z sub I, the input impedance, will be v1 over I1 in this loaded condition, or in this terminated circuit. What is our input impedance? So if we think about this, we need V1 and I1. Well, we have V1 and I1 in equation 1, but we have I2 sticking out there, and I2 is not necessarily 0. So somehow, with all of these other equations, we need to back out or obtain a way of rewriting I sub 2 in terms of V1 and I1. We want to find one equation that only possesses these variables V1 and I1 and all of the other parameter values, but no other variables I2 and V2, V sub G. Well, V sub G could be present, but we don't want V sub 1 and, V sub 2 and I sub 2 in any of our relationships, because we're now trying to find, or in this final equation, we're trying to take the ratio of V1 over I1 to find the input impedance. What we're trying to do then, in fact, is eliminate this second current, I sub 2, from equation 1. And we can't just set it equal to 0. We have something going on. We have a load attached, so there's current flowing in that circuit. But what we can do, in equation 4, we have a way of relating V sub 2 and I sub 2, and equation 2 has V sub 2 and I sub 2 in it. So maybe now, if we put equation 4, which is an equation for V sub 2, if we replace that v sub 2 with this formula in terms of I sub 2, now we have one equation that only possesses I sub 1 and I sub 2. We can solve that for I sub 2, and now we have a formula for I sub 2 in terms of I sub 1. Did you follow that? So what I'm trying to do is I'm going to use equation 4 in equation 2 and solve for I sub 2. I sub 2 in terms of actually I sub 1. So equation 2 is this v sub 2 is equal to z21 I1 plus z sub 2 to I sub 2, but equation 4 is Ohm's law, or that's now minus z sub L I sub 2. Or what we now have is minus z sub L I sub 2 is equal to z21 I1. Keep me awake, make sure I'm not writing incorrect subscripts. Z sub 2 to I sub 2. And now there's our one equation possessing only variables I sub 1 and I sub 2. So we can now isolate the I1s and the I2s on separate sides. We can say we have minus z sub 21 I1, putting that on the left, or subtracting that from both sides. And let's add z sub L I sub 2 to both sides, and we now then have z sub 2 plus z sub L, all scaling I sub 2. And that now allows us to solve for I sub 2 in terms of I sub 1. I sub 2 is now minus z21 I1 over z sub 2 plus z sub L. That's going to help because now we can use this formula for I sub 2 in equation 1 to eliminate I sub 2. Let's now use this expression for I sub 2, use this equation in 1, where this equation is that formula. Doing that, we then can rewrite equation 1 as V1 is equal to Z11 I1 plus Z12 times what we just had for I sub 2, this equation, minus Z21 over Z22 plus Z sub L times I sub 1. And let's simply combine or factor I sub 1 out of both of those pieces, and we have Z11 minus Z12 Z21 over Z22 plus Z sub L times I sub 1, and that really is just Zi I sub 1. That's just our input impedance times I sub 1. Or going ahead and finding the ratio, Z sub I is now equal to V1 over, where here is V1 over I1. So divide both sides by I sub 1, and we end up then with Z11 minus Z12 Z21 over Z2 plus Z sub L, and that's now our relationship for the input impedance of a terminated two-port. And that you can find, hopefully, in table 18.2 as one of the 6 characteristics of a terminated two-port in terms of Z parameters. And you can also find in that same table these 6 characteristics in terms of the other sort of 6 two-port parameters that exist. The Y parameters, the H parameters, the G parameters, the A and the B parameters. All of those are then available to find these different characteristics, gains, current, and voltage, Thevenin and voltage and Thevenin impedance, the output current, and the input or input impedance or input admittance for a terminated two-port. And that now simplifies the analysis involved in trying to analyze what's going on if we now have a terminated two-port circuit.